Okay, so we have learned a number of properties of composite vector spaces. So we will use those properties in the second postulate of quantum mechanics. Okay, so this is quantum mechanics. Postulate 2. Alright, so the second postulate of quantum mechanics is about composite systems. Alright, and we will use composite vector spaces to describe composite systems. So suppose I have a system, two quantum systems. I have a quantum system A and a quantum system B. Alright, then I want to describe the combined quantum system A and B. Okay, alright. In the first postulate we talked about isolated systems. Okay, in the first postulate we specifically talked about isolated systems, where the system we were considering was not interacting with anything else in this universe. So in a composite system like this, is the system A isolated? Is it isolated? Well, no, it's not, because it is interacting with B. Alright, it is interacting with B. Similarly, the system B is not isolated either. This is also not isolated, because B is interacting with A. However, the combined system is isolated. Combined system A and B. Okay, the combined system A and B is not interacting with anything else in this universe. Okay, so the combined system is isolated, but the individual components of the system are not. So if we have two systems A and B, if we have two systems if we have two systems A and B such that the combined system AB is isolated, then the state of AB can be represented as a vector of the composite space. Composite space, or the tensor product space of A and B. Alright, so well, that is the postulate 2. So in postulate 1 we had a simple system. We had a simple system, an isolated system, and the state of a simple system can be represented as a vector of a Hilbert space, and the state of a composite system can be represented as a vector of the composite Hilbert space. Okay, of the composite Hilbert space, or the tensor product space of the individual Hilbert spaces. Alright, so suppose I can have a state of the system AB. Suppose I can have a state of the system AB of the form, oh, definitely this vector needs to be unit vector. I missed that part, but that is definitely very crucial. Unit vector of the composite space. Alright, I can have a vector psi AB of the form like this. I can have 0A tensor product of 1 by root 2 0A plus 1 by root 2 0B. Alright, and this is actually, as you can see, this is a product vector because I have a vector of the system A times a vector of the system B, and the product vector is the vector of the system AB. Similarly, I can have entangled vector as state vectors as well. Suppose I can have a state of the combined system AB like this. You can have 1 by root 2 0A 0B plus 1 by root 2 1A and 1B. Okay, so this is an entangled vector, and we say in such a case, if the state of the combined system is an entangled vector, we say that the individual components are entangled. Okay, in this case we say that A and B are entangled. A and B are entangled, and we call this phenomenon entanglement. Okay.